The main topic of this screencast will cover Nernst potential and the properties of an action potential. Before we get into that, let's first discover what it takes to have normal resting potential. So I'm going to steal this picture from Wikipedia. 1 second. Okay. So let's consider this picture right here. On the left-hand side of this picture, assume that this circle represents a cell membrane. The cell membrane, for the sake of argument, let's say is permeable to the potassium ion. However, it is impermeable to the proteins that have a negative charge on them. Therefore, potassium is able to freely leak back and forth across this membrane, whereas the protein with the negative charges cannot leak through this membrane. Also, let's assume that the concentration of potassium inside the cell is way higher than the concentration of potassium outside the cell. Therefore, since potassium is freely able to move in and out of the cell, potassium will start leaking through the cell membrane out of the cell. This is shown in picture number 2 in the middle. As potassium is leaving the cell, the positive ions inside the cell are depreciating through time. This means that the proteins with negative charges are starting to accumulate with relative to the positive ions inside the cell. This negative charge inside the cell makes it less likely that this positive cation will continue to start leaking out of the cell. So the chemical gradient driving potassium ion is represented by this green arrow, and the electrical gradient represented by the negative electrostatic potential difference across the cell membrane is represented by this red arrow. Soon there will be a time where the concentration gradient that favors the potassium leaving the cell will be equal to the electrical gradient favoring the potassium from leaving the cell. This is represented by the Nernst equation on the right. The right side of this equation shows the chemical gradient, or the green arrow, and the left side of this equation shows the red arrow, or the electrical gradient. Let's use the Nernst equation to understand the situation on the left. The Nernst equation is given by E, or the voltage, is equal to RT over ZF times the natural log of concentration outside the cell over concentration inside the cell. Since RT and F are all constants, they can be simplified to 61. Therefore, the voltage is equal to 61 times the charge of the ion we're talking about times the log of its concentration outside the cell over inside the cell. In this situation, we're talking about the potassium ion. The potassium ion has a charge of positive 1. Therefore, the Z in this equation will be positive 1. Furthermore, we stated that there is more potassium inside the cell than there was outside the cell. Therefore, let's assume that for every 1 potassium ion outside the cell, there's 10 potassium ions inside the cell. So the fraction here would be 1 outside the cell over 10 inside the cell, or 1 over 10. The log of any fractional value is a negative number. So the log of 0.1 is about negative 1. This means that enough potassium ions will leave the cell until at one point the inside of the cell will be equal to negative 1 volts with respect to the outside of the cell. When the cell is about negative 1 volts, there will not be a net movement of potassium in and out of the cell. Potassium ions will still continue to leak back and forth through the cell membrane. However, there is no net movement of potassium out or into the cell. In this example that we looked at, we stated that there was a lot of positive ions inside the cell compared to positive ions outside the cell. But how did the cell get here in the first place? In order to understand that, we need to understand the sodium-potassium ATPase pump. The sodium-potassium ATPase pump essentially sits here on the cell membrane and pumps out 3 sodiums, 3 Na plus out, for every 2 potassiums in. The 3 for the number 3, the Na plus for 3, and the OUT, which is also a 3-letter word, for every 2 K plus, which is 2, in. This creates a lot of sodium outside the cell than sodium inside the cell. Furthermore, this creates a lot of potassium inside the cell than outside the cell. Let's look at some normal values. The sodium inside the cell is about 10 millimolars, and the potassium inside the cell is about 120 millimolars. the sodium outside the cell is about 145 millimolars, and the potassium outside the cell is about 4.5 millimolars. The exact numbers are not important. What is important to realize is that the sodium outside the cell is greater than the sodium inside the cell, and that the potassium inside the cell is greater than the potassium outside the cell, and this concentration gradient is maintained by a sodium-potassium ATPase pump. Since the sodium cations are more outside the cell than inside the cell, the Nernst potential for this sodium ion will be a positive number. And since the potassium ions are more inside the cell than they are outside the cell, the Nernst potential for potassium ion will be a negative number. If the cell were only made of sodium and the concentrations of sodium outside the cell were about 145 millimolar, but the sodium outside the cell was only 10 millimolar, then the equilibrium potential would be 71 millivolts. That means at 71 millivolts, there would be no net influx of sodium from the outside the cell to the inside of the cell. The same goes for potassium. At negative 88 millivolts, there would be no change in directionality of potassium from inside the cell to the outside the cell. We've also thrown calcium in here. Calcium is found at a really low rate inside the cell compared to the outside the cell. Therefore, it also has a really positive equilibrium potential. The way action potentials are created are essentially opening and closing of gates that allow the ions to move in and out of the cell. Let's assume that the inside of the cell is on the left-hand side and the outside of the cell is on the right-hand side. Furthermore, let's assume that this middle line right here is a gate that can be opened and closed. This is the doorknob. If this gate is open and these two gates are closed, then the cell will move towards 71 millivolts. Once it reaches 71 millivolts, there will be no net transfer of sodium inside and outside of the cell. Therefore, sodium will continue to move from inside of the cell to the outside at the same rate that sodium will move from the outside to the inside. The way a cell delivers its action potential is by opening and closing of selective channels that allow the movement of these ions. This is the typical action potential for non-automatous cardiac tissue. Stage 4, the resting potential, is because the conductance of the potassium ions are greater than these two gates. Therefore, the potassium ion is able to leak back and forth. Therefore, the equilibrium potential or resting potential will be closer to the potassium ion equilibrium potential. Due to a sudden event, what ends up happening is that this cell is going to reach a threshold value. Once this threshold value is reached, the sodium ion gate opens and the potassium and calcium ion gate continues to stay closed. As the sodium ion gate opens, sodium will quickly go from outside the cell to the inside of the cell, allowing the cell to try to reach the equilibrium potential for the sodium ion. This explains this depolarization right here. Afterwards is the plateau phase. During the plateau phase, both the calcium and potassium gates are open, but the sodium is not. Therefore, the calcium gate opens, the potassium gate opens, and the sodium gate closes. In this case, calcium ions will quickly go from outside the cell to the inside of the cell. At the same time, potassium ion will go from inside of the cell to the outside of the cell. Therefore, both positive ions are leaving and entering the cell membrane. This creates a plateau. Finally, the potassium channels continue to remain open and the calcium channels close. So closing the calcium channel and opening the potassium channel, allowing the cell to reach the potassium equilibrium potential again, making the cell go back to its resting potential. In essence, this is how an action potential is created, by the opening and closing of these gates, allowing the cell to reach the individual ion's membrane potential, or equilibrium potential. Thank you for listening.